Welcome to CAENexus demo. CAENexus automates CAE workflows, that is both CFD and FEA workflows from CAD till report generation. To automate these workflows, CAENexus takes two inputs. One is an abstract model file, which you are right now seeing on my screen. It has 4 tabs like meshing, which has all mesh related attributes, solution strategy, which has all solver related attributes, problem definition, which has element set, load conditions, constraints, etc. and output, which has all post-processing related attributes. So this abstract model file is authored by a PA analyst. The another important input for the automation is the PA CAD model prepared for the simulation. So this is a parametric CAD model which has all the features like extrude, round, etc. So this is not a dumb CAD. Along with that, it has certain parameters or tags like SCOM, which stands for simulation component, and S-class star, which stands for simulation classes. So SCOM represents product name and S-class represents simulation physics. So these are the two inputs. We'll get back to these two inputs once again. But before that, let us see how our customers are using this automation in a quick way. So this is the input XML published by Novus Nexus. It has two important inputs. One is abstract model block, which is same as abstract model file. The different blocks built up the final abstract model file. So this is the block name, and the CAD, which is the CAD geometry with Creo and 7.0, which we are using right now for the simulation. So this is a simple text file, and user needs to change these two parameters. And after that, user will start this CAENexus command prompt, and here user will give the first command, which is cn autorun minus prep. So this command will take that XML as input. It will fetch the CAD. It will take the AM block, and it will export the solver deck. So here prep stands for pre-processing. So now the process is running. It will take some time. Okay, till that cn autorun minus prep process works, let us review these two inputs for automation in more detail. So as said, the first input is abstract model file. It has different classes here, which represents physics. For example, here there is a solid class, which has a dimension. And at the moment, this is just a string, and it has the child items like boundary, interface, etc. So there are some volume classes. There are some surface classes like shell 2D, well 2D, etc. As well as there are certain relations like merge, or siloed face, solid, etc. Or let us say relation between fixed face and solid. So let us see what these classes are with this very simple example. So here there is a box, which is a gray box, and if I tag it as a solid, then the solid class will represent all this geometry. Boundary of the solid is all the faces of this cube. Let us say there are two boxes like red box and gray box, and both I have given the tag as a solid in the CAD. Then interface of solid is the common face between these two boxes. Let us take this third example, which is the solid and this red plate as a shell. So I have given solid tag here and I have given shell tag on red plate. So the relation between solid and shell is this common edge between these two entities. So this is a simple concept I tried to explain with a simple model. So at the moment, this abstract model file is not combined with any geometry. So once it is combined, then solid will start representing the specific geometry. So let us review certain attributes. One of that is base size. So here this mesh size attribute is given on the solid class, and the value I'm saying to fetch it from the CAD with the parameter mesh underscore size. So this is about the mesh size attribute. Let us take another attribute, which is surface mesh type. We all know that shell needs the chord dominant mesh. So the attribute mesh type chord dominant is specified on the shell 2D class. Solution strategy has all the solver related parameters and the settings which are defined on the global. For examples, whether to check it or not, which are solver parameters, etc. Or the analysis types. For example, here we are choosing static analysis, etc. And then let us review some problem definition attribute. So here there is first attribute, which is a solid. Element type is solid 187, which is specified on the solid class. And the material I'm saying, again, import it from the CAD with the parameter name mat underscore name. So this is about the solid attribute, and this is ANSYS mechanical abstract model file. Anyone who knows the ANSYS mechanical knows what is a solid 187. All these terminologies are picked up from the ANSYS solver. So user is not learning anything new. Similarly, shell attribute is there, which is defined on the shell class. Again, it has different element type, which is shell 181. And we are saying that fetch the thickness value from the CAD with the parameter shell underscore thickness. Then there is the load specified on the relation between C load phase and the solid. And here I'm asking to fetch the force values from the text file, which is load.xml. So this is about problem definition. Let us see some output attributes. In the output attributes, we are giving which is the solver, what is its path, which is the post-processing software. Here I'm using vCollab, but along with that, ANSYS Workbench and Hyper-V is also supported. Here we are giving vCollab paths, so that report will get generated automatically once all this process gets finished. There are certain other attributes like contour attributes. For example, here we are saying that define these contours on the attributes like node print and element print, as well as its layout, keep it, and camera view, keep it as a default. So these node print and element print are standard attributes that we always define as a part of post-processing. For example, this is the element print attribute, which is specified on the whole model. And so basically, I need to tell you is that we are setting up the report right from the abstract model itself. So this is all about abstract model file, which is authored by a FEA analyst. So this is the first input. Yes. So now we can see that our first process, that is CAENatorrun minus prep, is successful. So let us start next command, which is CAENatorrun minus solve. So solve stands for solving the deck that has been exported by this prep command. So let me show you the deck that has been exported here. So you can see here linker.cdb that is exported from the first command, and this is my input deck. So now you can see that all the nodes that have been exported here has numbers. So all the sets that those have been exported. And at the end, you can see it is asking to solve D here. D stands for degrees of freedom. So this is as per the ANSYS mechanical syntax. So this is my first command that has ran successfully. So my second command I'm giving, which is CAENatorrun minus solve. So it will start the ANSYS. It will take this deck, which is prepared, and solve it. So till it runs, let us see the second input here, which is the CAD model. So here you can see this is the FEA CAD model prepared by CAD specialist. This is the parametric model which has all the features. So this is not a dumb CAD. So here you can see it has features like extrude, round 2, etc. It has certain tags such as SCOMP, which stands for component name, and that represents the product name. For example, top FPA, we have given the same name, top FPA, RHFPA plate, which is the same name like RHFPA. Similarly, it has classes like S class. So you know any FPA simulations has solid or a shell 2D or a body, which is body just a dummy part. Then it has a mat underscore name, which is different materials like steel 1430, steel 2340, etc. So if you remember this mat underscore name, we have referred back in the abstract model file in the problem definition. So here, if you remember, we have said that import the material on the solid with the parameter mat underscore name. So this is what we have given it here. Then S class type is a specific type of that solid like pivot or weld or pin, bushing, etc. Then S class BC is about the boundary condition like fixed space, which is saying that this dummy part is going to fix that particular location, or C-load phase, which is about concentrated load. Then it has a contact, S class underscore contact, S class underscore merge, which is about sometimes we need to give number of nodes as 1 to merge to specific phases. That is represented by S class underscore merge. Then connector is there, which is about 1D stuff. Mesh underscore size is there, where different mesh sizes have been specified, like 45, 75, etc. Again, if you remember our abstract model file and mesh size attribute, then here we have given mesh size on the class solid, where the attribute is fetched from the solid class with the parameter name mesh underscore size. So that is being specified here. Last shell underscore thickness, where those are the shell parts we are specifying thickness, and this parameter is also fetched in the abstract model file. So this is all about the CAD model that is being prepared. You need not to give all these tags manual. We have Excel, where user can export the blank file, can quickly give those tags and import this Excel file back in the abstract CAD model. So this is not more than 5 minutes job. to write the Excel and import it here. So this is all about the second input. So you can see our second process, that is CAENatorrun minus solve, that is also successful. So now I'm running my third process, which is CAENatorrun minus post. So post stands for post processing, and it will generate the automatic report from all the inputs that we have given in the abstract model file. So this is my third process that is going on. It will take some time. So let me show you that once this abstract model file is ready, once this CAD model is ready, the next step is about the combining, where I'm choosing the CAD model. So here I have chosen this dozer assembly, and it will start creating the simulation model. So it will take some time. Till then, let me show you how it looks like. So here, this is already, I have created the simulation model. So now if I click on the class solid, it will start highlighting all the solid parts, which are here. Then let us review some attributes. For example, mesh size, it is on the solid, and we said fetch it from the CAD with the parameter name mesh underscore size. So it will go from class to model tab, and now you can see that this is the mesh size attribute. It is going on each region, and it has all the values like 45, 75, 55. Those have been fetched from the CAD. Similarly, let us review another attribute like material, which is specified in this element set attribute. So now you can see it under solid. Every solid, this attribute has been transferred from the solid class. So let us review one of that. And now you can see solid 187 is there. And now you can see material steel 1430 that has been fetched from the CAD body. And if you click here under on steel 1430, here it will start highlighting which part has steel 1430. And if you click on steel 2340, it will tell which parts have steel 2340. So this is all the attributes. Those have been transferred to the real geometry. Then the next step is to click on the mesh model, and it will take all these mesh parameters which we have defined in terms of mesh size, mesh order, mesh curvature, and it will generate the mesh. So now I have generated it to save the time. So you can see this is the mesh model that is being created. And finally, we are doing the export. So this is what I showed you right now through user interface that is being done automatically through our command CAENatorrun minus prep. So let us see. Now you can see our third process, that is CAENatorrun minus post, that has been executed successfully. So it has prepared the report here, pushbeam.ansys.html. So let me open and review it. So this is the title page of the report. Then it gives a model summary, like which abstract block is used, which CAD is used, solver name, material name and its properties like density, etc. All the component names versus its material. So all this data is there. Then inputs of the simulation, those are stated here, like concentrated load, in which set it goes, what are its values, etc. And finally, it has outputs like displacement in the model, stress and strain that is in the model. Besides that, it gives the model views, like for example, what was your model, which you can see it here. You can rotate it, zoom in, zoom out, and do all the things. Then mesh view, what kind of mesh that is being submitted for the simulation. Then it gives load step details. First one is a displacement. So it gives you maximum 5 points in the displacement here. And here you can do the animation also, like how this uh, displacement has been applied. So this is that stuff. Then you can see stress details also, like where there is the maximum stress, all the 5 points, those have been specified here. The stress is maximum. Those points will be located. Similarly, strain data is given. So this is the VCOLAB HTML report. Similarly, we can prepare ANSYS Mechanical as well as Hyperview PDF or PPTX report too. So this is all about all the 3 steps and automatic report generation by C. Now we have seen the 3-step automation process till the report generation. Here I'm showing the completely different model. This geometry is completely different than earlier push beam model. But you can see I have given same S classes like solid, body. Here material names are different, steel 1430, etc. Type is weld. Then there are certain boundary conditions, load point, fixed space, and mesh size. Here different mesh sizes than previous one. So we can still use the same abstract model file which is given for the push beam model. This is because we have specified all the attributes like mesh size, or let us say solid element set on the classes which represents physics. So these attributes are on the solid, shell 2D or merge class or the model, and those are common between the two problems. So this abstract model file will become reusable. So let me show you how its simulation model will look like. So here, if I click on the solid, now it will start highlighting different solids, which is specific to this problem. So all the solid element set or solid 187 attribute will go on these solids. Or let us say uh, in this problem, there is the body. So here it will start specifying bodies which are being used to specify these constraints. So now we can see that our abstract model file advantage, the first advantage is that it has reusability. You can use it across different problems once you keep your simulation classes same or organization defined. So abstract model files are reusable. Second advantage is you can capture all the analyst's knowledge in a very small file, which is abstract model file. And that file is not more than 5 MB file, which you can keep it. You can transfer this file to less experienced simulation engineers and analysts, which can start the simulations, so that democratization of simulation is achieved. The another advantage is that because this process can be driven automatically, you can run the simulation almost 24/7. Most of our customers have achieved the productivity improvement in terms of 5 to 10 times. So this is all about the advantages of abstract model CAENexus and its automation process. So here let me show you how you can run CAENexus through the process management software by creating a simple web applications. So here, this is one sample web application that we have created. where you can choose the CAD modeler, you can choose the geometry, or you can upload it, you can choose the solver, measure, you can choose the post processor, and just to submit the job, which will run those three commands, which I explained to you at the start of demo. That is CAENatorrent minus prep, solve, post, and that will generate this automatic report. So here you CAENexus will run in the background. In the front, this is a simple web UI that is being given. I'm showing another CFD application which is created specifically as a custom application for the HVAC simulation. So here it is more customized, where you can give different panel modes, temperature modes. So this is for designers, and here also user can submit the simulation by selecting the CAD geometry. So if you create these custom applications, then you can just submit it and CAENexus runs in the background, and overall the report will be obtained by running all these processes. So this is all about CAENexus automations and its three-step processes and how we can improve the productivity at your organization. For more questions or information, please write us at support@novusnexus.com or visit our website www.novusnexus.com. Thanks a lot, and I hope you have enjoyed this session. Thank you and have a nice day.